In this lecture, we take a look at an aspect or an application of physical chemistry. Back in our unit on work and energy, I described to you what is meant by chemical potential energy. Chemical potential energy is energy based upon the positions of atoms, for example, within molecules. When molecules are formed, work has to be done against electrostatic forces in assembling the atoms into a molecule. So here is a bare bones calculation, if you will, a bare bones version of that, involving, for example, finding potentials associated with a series of point charges. Okay, I've assembled this problem into a question for us. Let's go ahead and access it here, copy it down into your notes. Calculate the amount of energy necessary to assemble a molecule consisting of 4 point charges, Q1, Q2, Q3, and Q4, that are arranged into a square of side A. The charges end up fixed in place. So the minimum amount of energy that's necessary to do all of this, to assemble the molecule, that then becomes stored in the molecule as chemical potential energy. Okay, what we do essentially is a process where we bring charges in from infinity, eventually assembling all 4 of the charges here in this case into a square. So what we'll do is start off with one of the charges as isolated in space, for example, Q1, and then what we do is we calculate the work done against the electric force due to Q1 by bringing in the second charge, Q2, from infinity. Here's how we do so. Okay, so right here, for example, is Q1, and then right here is going to be a point P in space that we're going to eventually place Q2. So then therefore, if this distance here is A, let's go ahead and find the potential at point B due to charge Q1. Okay, so that potential is just going to equal Q1 over 4 pi epsilon naught multiplied by the distance A. And then what we do is we bring a second charge, in this case Q2, we bring it in from infinity where we start off with a potential of 0 and then end up right here where the potential is this value. So now let's go ahead and place Q2 here on the diagram like so at point P. And then let's go ahead then and calculate the change in potential energy as we come in from infinity where the potential energy is at 0 and then end up right here. So then therefore we calculate that very simply in the following way. Change in potential energy per charge, in this case Q2, is equal to the potential difference, final minus initial, where the initial potential energy is at 0 because that's the potential at infinity. So then therefore we have the change in potential energy as Q2 times Vp. Change in potential energy is the final value minus the initial value of 0 at infinity. And then therefore, the amount of potential energy that is now stored in these 2 charges is the following expression. Like so. So far the energy necessary to assemble these 2 charges is Q1, Q2 divided by 4 pi epsilon naught times A. Okay, let me do a little bit of erasing here. Like so. Okay, and now let's begin to think of bringing in the third charge from infinity. We're going to place the third charge right over here at this point in space, which is a distance A away from Q1. And then this distance right here can be found by doing a little bit of Pythagorean theorem with these values. This distance here from Q2 is going to be root 2 times A. Okay, now let's find the potential at this point here. Once again, we'll call it point P due to these 2 charges, Q1 and Q2. So this is where we use our series of point charge calculations in order to find the potential at point P. We basically just add the expressions together. So first of all, for Q1, a distance A away. So Q1 over 4 pi epsilon naught times A, plus then Q2, which is a distance of root 2 times A, like so, from point P in space. And then just like I did earlier for this first calculation, essentially what we then do is we take this quantity here and we then just multiply it by the Q3, which we now place at this position here. Once again, we're bringing in Q3 from infinity where the potential is at 0 and it begins with a potential energy of 0. So then therefore, when we do bring it in from infinity to this point P in space, now the amount of potential energy stored in the molecule is the following. It is equal to Q1, Q3, divided by 4 pi epsilon naught times A, plus Q2 times 3, Q3, divided by 4 pi epsilon naught times root 2A, but then also plus this previous value here. This, of course, represents the work that we have done already. Like so. So now we end up with a total of 3 terms for these 3 charges that have been brought into this position. And then we just essentially repeat this process now for the last charge. Okay, so now the last charge is going to be brought to this position here. This position here is now going to be our new point P. Its distance away from Q3 is A. Its distance away from Q1 is root 2 times A. And its distance from Q2 is A. So now let's go ahead and find the potential at that point due to these 3 charges. So that's going to be, first of all, we'll do Q1, which is a distance of root 2 A away. Okay, and then Q2, which is a distance of A away. And then lastly, Q3, which is also a distance A away. Like so. Okay, and then we take that quantity and we multiply that by Q4. That's when, once again, we bring Q4 in from infinity to this position here on the diagram, like so. So now the total potential energy stored in the molecule is going to be Q4 times all of this, but then plus all of this, of course, the work that we had done earlier. So let me just go ahead and add on the terms to this quantity here from earlier by basically taking this expression here and multiplying it by Q4. Okay, so very simply, we then end up with a plus, and then from the top, Q1, Q4, 4 pi epsilon naught root 2 times A, then Q2, Q4, over 4 pi epsilon naught A, and then lastly, Q3, Q4, over 4 pi epsilon naught A, like so. So to assemble this square of 4 point charges into this molecule, we need a grand total of, as you can see here, 6 terms. This is then therefore the potential energy stored in the molecule.